Hello, my name is Atharv and I'm part of the team 19853, the Roboteers. Today I'll be explaining TensorFlow. So to really understand TensorFlow, you have to understand autonomous, which is the primary reason we use it. Autonomous is a part of the game where the robot has to drive by itself for 30 seconds with no human input, only sensors and whatever's been programmed for it. So, in one of our missions is to detect which face a cone is facing towards us, and go to a space determined by which one it is. So we can go to one of three options, and there's three signals on the cone. So TensorFlow is an AI framework made by Google um, to train neural networks, and you can use it for object detection, which is the primary reason we use an FTC. So FTC has provided us with the custom with their own model for the sleeve that they made for this year, and we can use that model to train our own to make our own autonomouses to go anywhere. So we first initialize all of our things. So we use TensorFlow and Vuforia. Vuforia is what we use to actually capture the image. It captures the image and passes it over to TensorFlow, who does all the stuff to figure out which one it is. And and as we do, we pass it to TensorFlow. And then once we figure out which option is best, we go to the square. We do this by a library called Roadrunner, which I won't explain much now because we have a separate video we're gonna record. But what it'll do is it'll go to a certain location very specifically, and we can go to that location using our TensorFlow output. Thank you.
Hello, my name is Rithvik Sharma. I'm on team 19853 on team Roboteers. Today, I'm going to be talking about Roadrunner. So Roadrunner is a type of motion planning library that helps the robot go from one point to another point. So many people use this type of program in their autonomouses, in FTC. So if you want to download Roadrunner, you go to learnroadrunner.com. So when you finally get here, you'll want to get to this introduction page, and here it'll tell you what Roadrunner is. Then we'll go to the before you start page. This is telling you basically some tips and what you should probably know. So then this page is probably telling you should probably be knowing like either Java or C++ if you want to do Roadrunner. So here it's telling about the installation of these methods. So there's one method of like downloading the quick start, and two, installing RR on your project. You can do either of those. Let me try and go down. Yeah, right. Yeah, see? So if you go here, you can install RR. So these are your two methods to choose. So once you do one of these, I'd highly recommend for you to upgrade your firmware on your control hub to your nearest update. And then you go to the high-level overview. Here, this gives you a graph where it tells you what you need to do. So this is basically like a flowchart of what you need to do in order for your Roadrunner to be successful. So, first of all, you need to declare if you're using drive encoders or not. After this, you're going to have to say if you use dead wheels or not. After this, you want to do the localization test and drive the robot around the field, which will allow you to find anything wrong with your bot's localization. After this, you'll do this tuner, which is called the Drive Velocity PID tuner. And it's used to tune the rev hub's built-in motor, velocity controller, and so it helps that. And then here you use the Drive Forward Feed Forward tuner, and it helps your feed forward constants get tuned. After this, use the straight test. It's basically the velocity PID tuner and feed forward tuner It sees how good it has done on like normal on like a normal like a mat almost. Then you do a tuner called a track width tuner. It's like the distance of one wheel to the parallel wheel, so like two wheels across. All this is like a measurement which will help the system know how far your wheels are. After this, you do the turn test to confirm that your track for your wheels is good. Then you'll do the localization test again, and then this time you basically see if your anything happened with the previous test and if your bot is able to localize. Finally, you'll do the follower PID tuner, and this will basically tune like the two PIDs, the heading PID and the translation PID. This allows you to get control and ensure accurate path following. So if you don't want your robot to be able in the competition to stay close to the path that you're following, it will help you. After this, you have to do this flying test, and you basically just set positions as you make your robot go to see if the entire set has done it. If it passes this flying test, then you're good. After this, going on to drive constants, I'm not going to go fully over it, but it takes about 6 per rev and max RPM. It also gives you more nice information that you could probably use for your Roadrunner journey. After this, it talks more about these tuners and tests in more detail in case if you need them. And then after this, it gives you an overview of how to build a trajectory in case if you need that for Roadrunner. And then it tells the different functions that you have while building a trajectory for Roadrunner. Finally, it tells you how to make a marker for Roadrunner, which is 2 points. If you want to put a marker down, then that's a point. Finally, it gives you an overview from trajectory buildings, and after that, and how to add trajectory and reset. And then finally, it gives you some advanced tips in case if you want to make your Roadrunner even better or learn something new. And then it gives you some tools and further resources in case if you want to ask questions. Thank you. My name is Rithvich. Please like and subscribe.
Hello everyone, my name is Mrinalai Rajiv, and I'm going to be talking about field-centric and robot-centric. The basic things which allow a robot to know what direction and which position it's facing is field-centric and robot-centric. Field-centric refers to the field, and wherever you place the robot, north pertaining to the field will always be north to it. So basically, to put things in perspective, north will always be north, no matter how the robot's facing. Just as we think that you are outside the court, perhaps over here, and you aren't driving inside the robot. Robot-centric refers to the direction the robot is first placed, so it can be anywhere, or even the direction that it's first placed. West in field-centric could be south or even north in robot-centric. It depends on the position direction that the robot is facing, once again. Field-centric is preferred over robot-centric in our competition because you need to have an open view of the field, and you don't really need to place yourself inside the robot. A basic example of robot-centric is when you drive in a car and you are inside of the vehicle. And field-centric is like a magnetic compass, and no matter where you stand, it will always face north. Two of our drivers, after an interview, like field-centric because they have an open view of our field, while our main driver prefers robot-centric because he can easily control it and can steer the robot better while inside. Thank you. I hope you learned something today.
Hello, my name is Ankur and I'm from Team 19853. Today I'm going to be talking about wheel profiling. So profiling is where we take in information, we record that data onto a graph, and then we analyze that data. And we do this so that we can spot problems or imperfections in our robot or other things. So why we did this? Why we're wheel profiling is because one day when our driver was driving our robot to practice, we noticed that when he pushed the joystick forward, the robot would move forward, but then it would be it was moving more towards the left than instead of going towards straight. So what we did is we sat down and then we talked together and about ideas to how we can fix this. And then our coach came and introduced us to wheel profiling. So then we started to work on that. So how we wheel profiled is we took our robot and we set it on top of 4 cones to unload it, and then we ran a program where it would make the motors run for 2 seconds for a given amount of power. So then we would plot that on a graph where for the x-axis we would put the amount of power, and for the y-axis we would put the amount of ticks. So once we ran the program, we would look at our driver hub, and then we would record the amount of ticks that our motors have rotated. So what happened, our results were, for our left wheels, we noticed that as the power was near 0 to 0.3, our left motors stopped turning entirely. Like they just stopped, they wouldn't rotate. So what we did to fix this is we added washers to adjust the bevel gears, which were taking the motor's rotational power and putting it to the wheels so that they would rotate. And then, so after that, we could start seeing improvement, or like our driver was more precise and he could get more cones in. So in conclusion, wheel profiling is it's very useful, and you can also, and it's not like only wheel profiling, you can also profile many other things. And thank you.
Hi, I'm Arjun from Team 19853. Today, I'm going to be telling you about our D-pad mechanism. Our D-pad mechanism brings our arm and Viper slide to the ground immediately. It also closes and opens our claw, which makes it very convenient to pick up the next cone. We built this in our 2023 Teleup code. You might not want to use this right after you drop a cone in a high junction, or else you might snap your arm. Of course, your mechanism could be completely different depending on what kind of robot you have. We have an arm and a Viper slide, which makes it really easy to implement this mechanism. This process is extremely fast, which makes it very easy to cycle and much more convenient than having to do it by yourself. The reason we made this was to make our lives much easier when we try to drop a cone, because before it would take at least 10 seconds itself to lower and close our Viper slide and our claw. Well, that'll be all. Thank you.
Hi, my name is Arush from Team 19853, and today I'm going to be talking about the touch sensor that our team put on our Viper slide. Before we put our touch sensor, our steel Viper slides would never stop going down after we wanted to bring it back down. Our steel Viper slides would always end up hitting our motor, which would eventually lead a scratch or a dent. This scratch or a dent, we realized, could turn into something much worse over time. So our solution that we came up with was a touch sensor. Our touch sensor makes it so, in fact, when the steel Viper slides come down, whenever it touches the touch sensor, it immediately stops instead of hitting the motor. This helped us a lot because in the future, if we didn't have this touch sensor, our motor would be severely damaged. Some facts about the touch sensor is that most of the times, the sensor records whenever it's being touched. But since this time we've put it on an object, it embraces the touch, as we've mentioned in the next point. While embracing it, it can set limits or stopping points. So as it embraces it, it tells the steel Viper slides to stop. And with this communication, it is considered an active process because of how the touch sensor is always ready to give commands to the Viper slides and tell it to stop. Overall, we thought this touch sensor was really helpful and made sure our robot would actively be still be working today. Thank you.